Hey everybody, and welcome to Data Science Foundations. So today we're going to be talking about a question that's maybe been in the back of your mind for a very long time, and that is, hey Nate, where's the linear regression? Most normal, quote unquote, data science courses start off with linear regression. Maybe that's their second, that's their third, fourth lesson or something like that. There's a couple reasons why we're not covering it too much. One of these reasons is, well, a couple of reasons why it's coming so late and why we're not covering it so much. So one of these reasons is there's tons of machine learning algorithms. Linear regression is sort of the shining star, the sort of the simplest and the most commonly used one. I will give it that, and that's why I'm actually giving it a place in this foundations course versus every other machine learning algorithm I'm not giving a place. With the exception of, I believe, random forest are mentioned. And there's a reason why I mentioned these two. These are two incredibly powerful ones. Notice how much foundational material we were able to cover without linear regression. An incredible amount. And a lot of this should be new, especially the bootstrapping and the plugin principle. What is the sort of nascent form of the bias variance trade-off that we mentioned in the previous class. So we've covered a ton of material thus far, and we really haven't needed to talk about linear regression. It's always been a little bit more complicated, always a little bit outside of, but now that we've got sort of our foundations of machine learning, which we can sort of check out here, this sort of chart, now we can sort of begin to talk about linear regression. A second reason why we haven't covered it is linear regression, at least in sort of a normal base class, in terms of normal distribution base class, has a lot of statistical underpinnings that we're not going to get into. And the reason we're not going to get into is because we haven't talked a lot about statistics. And the reason we haven't talked a lot about statistics is I believe you can get the foundations of data science without knowing a ton of math or statistics. So for that reason, we really haven't gone over it. But now it's sort of important to go ahead and go over it. We're going to be using it as a tool for teaching for the rest of the class, so we may as well do it here. So let's get started. When we're talking about a new machine learning algorithm, or a machine learning model is, I guess, the appropriate thing to say, there's a couple things that differ. So we have a machine learning model is both the inputs to the machine learning model, so specifically, can it take quantitative inputs, can it take qualitative inputs? It is the error measure, it is the learning algorithm, it is the hypothesis set, and it is the final hypothesis. These set of things are sort of all bundled together to create a machine learning algorithm, a model. Now, this is not to say that you can't measure different errors from any specific machine learning model. So specifically, when I make models for my day job, I measure a couple of different error measures because I'm interested in a couple of them. And this is not to say that any of these are super binding. You can change hypothesis sets fairly easily. But this gives us a good framework to think about machine learning algorithms. So let's go ahead and let's talk about linear regression. So, to specify linear regression, we're going to be taking a little bit of a shortcut, and we're only going to be specifying the error measure, the hypothesis set, and the learning algorithm. The inputs to linear regression are pretty nice. Linear regression takes quantitative features. That's the only thing it can take. So you need to make sure to convert all of your quantitative feature or all of your qualitative features into quantitative features before you do this. When I go ahead and make the practical data science lectures, which will be sort of a link up here for the practical data science lectures, which hopefully will be in the next couple of months, maybe a year. We're going to talk a lot more about machine learning algorithms, but here we're just going to keep it simple. So let's get started. Linear regression has the input that is quantitative features, and it has the output that is quantitative features. So its only output is quantitative features. If you're interested in a qualitative feature, then this is not for you. You need to use something different. So yeah, obviously the error measure, it's going to be something specific to quantitative features. In this case, it's going to be mean squared error. So that's the error that we're using in linear regression. There are reasons why we use this error. It doesn't really matter too much why we use it for you. Just note that this is the error that the learning algorithm will seek to minimize. The hypothesis set. So here's where the sort of the big thing comes in. In linear regression, just as in all supervised learning problems, we'll have a set of factors. And with linear regression, the set of factors, the hypotheses, will have the form of W0, a weight, times your first feature. This might be the size of petals, plus W1, so another weight, times the second feature, which might be the width of the petals or something like that. So if you had two sort of features or two factors, some possible hypotheses could be 2 times x0 plus 3.4 times x1, or 0 times x0 minus 100 times x1. So notice, what we're basically doing is we're taking all linear combinations of the features that we give it, and that is linear regression, which is why it's called linear. The reason why it's called regression is because originally it was used to sort of prove this idea of regression towards the mean, which is sort of an interesting idea, but it's a little bit outside the scope of this class. So, cool. You're like, okay, I get it. Any linear combination, that's the set of hypotheses. So we just have our computer look through all linear combinations of things. Oh, wait. The W's could be any real number. That means we have infinite hypotheses. Whoa. So there's some problems here. So if you remember previously, we were talking about this sort of trade-off. And this trade-off happened to be that, hey, there are unlikely events, and these unlikely events are hypotheses misrepresenting themselves. The more hypotheses we try, the more likely one of these unlikely events will happen. A hypothesis misrepresents itself to an extreme amount, and we get some hypothesis that is absolutely correct, right? It is perfect. We get a perfect hypothesis, and if we use our learning algorithm, to find the best hypothesis, it would find this best hypothesis, the one that misrepresents itself, and it would select it, and we'd get that one, and this hypothesis, by definition, misrepresents itself, so it will do really well on our sample data in the training set, but it will do terribly on the test set, and then we'll be quite sad. Well, that is certainly a concern. But there is sort of a saving grace here, and this is something that we're not going to be going into too much because it's incredibly theoretical. But let me ask you a question. How different are these two hypotheses? Hypothesis number 1, 1.00001 times x0, and hypothesis number 2, 1.00002 times x0. Not too different. In fact, they're pretty similar. It's probably not going to change your predictions by too much at all. So, what does this kind of entail? It kind of entails that we don't really have infinite hypotheses. Yes, there are infinitely many hypotheses, but most of the hypotheses are so similar to each other that they don't really even matter. Now, don't take this as a proof. This is not a proof. I'll go ahead and I'll include a link up in the top that will show you necessarily a pretty good proof of this type of concept. But let me at least tell you the rule of thumb that you should get out of this. So, a responsible data scientist will, for every infinite parameter in their model, have at least 10 data points to train their model on. Okay, so this is what a sort of a general reasonable data scientist will do. So if we had a model that was W0 times X1, so we've got one weight that could be anything, we should have at least 10 data points. For W0 times X0, to Wn times Xn, we should at least have n plus 1 times 10 data points. So, okay, there you go. You've kind of learned linear regression. But the last thing, and this is another sort of crucial point. So for learning algorithm in linear regression, you might be wondering, well, Nate, I kind of get what you're saying with infinite hypotheses, but how do we even search through infinite hypotheses? I would imagine searching, even if we were searching really fast, it would take 1 second or one millionth of a second times infinite time, which turns out to be infinity. Well, so the idea here is that the learning algorithm for linear regression is pretty simple. It turns out that there's a programmatic way, so there's a mathematical way to instantaneously derive what the best hypothesis will be. We're not going to get into that. Of course, you might be like, wow, Nate, this is really sparse, but it's not really important. The one thing you need to know about the learning algorithm is it does always return the best one. So you run linear regression once and boom, you get the absolute best one, best hypothesis, best linear combination of your features. The second thing you need to know is that the learning algorithm is exceptionally fast. It's very, very fast. It's blazing fast. It's probably one of the fastest learning algorithms with the exception of k-nearest neighbors. Okay, so we've learned linear regression. This is our first sort of infinite hypothesis set that we've sort of dealt with. And I've done a lot of hand waving here, but there will be some things that I will not do hand waving for, and this will be down below. So let's go ahead and do our first real learning problem. I've gone ahead and I've downloaded a data set here, and this is the Seaborn data set. It's the one that they use sort of for their visualizations, and it is a tip data set. What it is, it gives you the total bill and what people tip, and then lots of things about them. So now one of the things that we should definitely do here is that before we go ahead and we visualize it, we should split it into training and testing. Again, because you don't want to sort of pollute your mental model space by looking at some of this data before you do so. So that's fine, but this is a test lecture. So we go ahead and we split it. Notice the test size I'm using here. I'm using 90% of my data goes to test, and this is for illustrative purposes. So this is our data. Not too much. We notice that there is some sort of line that goes sort of straight up here. They look pretty related. Well, so obviously the total bill would be pretty related to the tip. Generally speaking, the tip is somewhere between 20 to 15%, and I might be crazy here. That's what I thought. And for those of you outside the United States, I know this is not true, but I think generally in the United States it's between 20 and 15%. Maybe it's a little bit less if you don't like the waiter or something like that. So I'll set make a set of hypotheses that the tip is, either is it 20%, 18%, or 15%. So I've got 3 hypotheses. I try them all. I get the best hypothesis is hypothesis number 2. It looks like people are cheap and their tip is around 15%. Okay, so I've got a mean squared error of this. Next, I want to go ahead and I want to try out our new machine learning algorithm. I want to try out linear regression, see what this does. Okay, so I go ahead and do linear regression. Notice the way that I fit it here. I actually have videos on the way that you fit these models, so definitely check those out if you're interested in the code. And I go ahead and I find the mean squared error. Well, lo and behold, the mean squared error for linear regression is 1.60, whereas the mean squared error for my prediction is 1.69. Notice the mean squared error is much less for linear regression, right? Well, not much less, but almost like 10% less, almost. Well, I guess it's 5% less. So anyways, a lot less, right, for linear regression. So linear regression is much better, right? Well, not exactly. If you remember, we've got this rare event, which is hypotheses misrepresenting itself. Is it more likely that a hypothesis will misrepresent itself if we try 3 hypotheses? Or if we try near infinite hypotheses? And the way that you'd think about this is that you look at the number of infinite parameters. So in this case, it's linear regression with 1 parameter, so that's 1. And you multiply that times like 10 or something, So in this case, it's very likely that our linear regression is going to be misrepresenting itself, or it's much more likely that it's going to be representing itself rather than our finite hypotheses are going to be misrepresenting itself. So how do we check if it's misrepresenting itself? We check the test data. So we go down, we check our test data, and lo and behold, yes, it turns out linear regression was misrepresenting itself. The error that we get from linear regression is a little bit more, about 2% more, maybe 1.5% more than in our finite score. Are we surprised? we're not super surprised. But we should start to notice this trend that's happening. The more hypotheses that we search over, the lower our training error will be. However, the more hypotheses that we search over, the more of a chance we get a hypothesis that misrepresents itself. The more data points that we have, the less likely we will get a hypothesis that misrepresents itself. So we get these sort of knobs as a data scientist that we can sort of play with up and down to sort of figure out which would be the best model, which would be the best set of hypotheses and learning algorithms in order to choose what the final hypothesis will be. So some takeaways here should be, yes, you can have infinite hypothesis sets, and the rule of thumb for everything but neural networks. So for basically the rule of thumb for linear regression, logistic regression, is that for every infinite parameter in your hypothesis set, you should have at least 10 data points. Okay. As always, if you're sort of new to this channel, I've listed some comprehension questions down here. They should be fun. Feel free to fill them out, sort of write them down on your own, and then check the comments below. If someone has answered them in the way that you've answered them, just go ahead and give them a thumbs up and check out what my response to their answer was. If no one has answered them before, or you're answering them in a novel way that you haven't seen people answer before, go ahead, put the answers there, and I'll go ahead and I'll put a little response. Okay, well, I hope you've enjoyed this lesson. I think as you notice, we're very much so building on ourselves each lesson. So definitely tune in for the next time. It's only going to get more interesting. Thanks.